This video is about arc lengths and areas of sectors. It's found in your text in section 11-6. Okay, here's some new definitions for you. An arc. An arc is part of a circle. We write this symbolically sometimes as arc AB, so AB with a curved line over it. An arc measure is the measure of an angle. It's the angle that we would have to make in the center of a circle in order to define this arc, which is part of the circle. A sector of a circle is a region bounded by two radii and an arc. So this gray shaded area is a sector of this circle bounded by this arc and these two radii. It's kind of like a slice of pie. And we would call this sector AOB. Okay, arc length is part of the circumference of a circle. Arc length is a measure, and it's going to be a measure in units of distance, because it's the distance that you would have to walk to get from point A around the edge of the circle to point B. So to avoid memorizing a whole bunch of new formulas, let's think of our calculations in this way. Arc length is a fraction of the circle's circumference. So the distance I would have to walk to get from here to here is just a fraction of the distance I would have to walk to get all the way around the circle. And if I can find what fraction that is, then I'm home free, because I can simply multiply that fraction times the whole circumference of the circle. Similarly, the sector area is a fraction of the circle's area. So this shaded region is just a fraction of the area of the entire circle. And if we can find out what that fraction is, we can multiply it by the area to get the area of this sector. So the last piece of information is, how do we find that fraction? Well, we find the fraction using the number of degrees in a whole circle, which is 360, and the number of degrees that is the arc measure, the measure of this angle that makes the sector what it is. So we take the arc measure over 360 and we multiply it by the circumference or area, depending on what we're trying to find. Okay, let's try an example problem. We're asked to complete this table. Since we know that we're dealing with sectors and arc lengths, let's start by drawing a circle. We're given that the measure of angle AOB, so A is some point on the edge of the circle, O is usually the center of the circle. Where's B going to be? 240 degrees is our angle measure, and we've not dealt with any angle measures that are more than 180 degrees before. So what we have to do is we're going to go around all the way to 180 degrees, and then we're going to keep going past 180 till we get to about 240 degrees. We're going the long way around this circle. So when we're asked to find the arc length, we have to remember that we are walking the long way around the edge of this circle to get from point A to point B. And that's going to be some fraction of the entire circumference of the circle. So what is the entire circumference of the circle? Well, we know from our formula that it's 2 pi times r, which is 2 pi. In this case, our radius is 3. So the entire circumference is 6 pi. What we want is some fraction of that 6 pi. The fraction comes from the angle measure, 240, divided by the entire angles in a circle, so 360 degrees, the angle measure of an entire circle, I should say. So that fraction times 6 pi, which is our circumference. We can simplify this a lot since 6 goes into 360 60 times. 60 goes into 240 4 times. So we end up with 4 pi as our arc length. Now we're asked to find the area of sector AOB. Now remember, we're finding the big area here, since our angle measure is more than 180 degrees. This is the part of the pie I'd want to keep if we were slicing up this pie. So what we're going to do is we have our formula for the area of a circle, which is pi r squared. So in this case, we have pi times 3 squared, which is 9 pi. And we want this fraction of 9 pi. So again, we have 240 degrees over the entire circle, which is 360, times 9 pi. Again, this simplifies down really nicely because 9 goes into 360 40 times. 40 goes into 246 times. So we're left with 6 pi as the area of this sector. You try one like this. Complete the table. Let's do another example problem. We're told that the area of sector AOB, okay, let's draw a circle again, and we're going to make this sector using point A on the edge, O in the center, and this time we're given that the measure of AOB is 100. So we want to go around the circle a little more than 90 degrees. Let's say that B is here, and this angle here was 100 degrees. The area of this sector is 10 pi. So this area, the number of squares it would take to cover this area is 10 pi. We're asked to find the radius. Okay, so this feels like we're working backwards. We're given the area and we're finding a radius. So what we can set up is that the area of the sector, I'm going to write A sub S, is equal to 10 pi. That's our given information. And we want to find the radius. So I'm going to set up this fraction. We know that 100 degrees is the measure of this sector. So 100 divided by 360 is the fraction of the circle that we're dealing with. So that times the area of the circle is going to give us the area of the sector. Now I know the area of a circle is pi r squared. So I have this fraction, which I would like to simplify right now. Crossing off 1 0 each, now I have 10 over 36, which reduces to 5 over 18. That's a little more manageable. 5 over 18 times pi r squared is equal to the area of the sector, but we're given the area of the sector. So that equals 10 pi. I can simply substitute 10 pi for the area of the sector. Now I have an equation that's pretty manageable. I can divide both sides by pi. Okay, and then I have 5/18 times r squared equals 10. So, or 10 over 1, really. So cross multiplying this would give us 5r squared times 1 equals 10 times 18, which is 180. So dividing both sides by 5, 180 divided by 5, I have to write my equation backwards here, is 36. So to finish my calculation, I have r squared equals 36. can take the square root of both sides of this, and I get a nice whole number for r. R equals 6, the square root of 36. You try this one. The area of sector AOB is 7 pi over 2. And the measure of angle AOB is 315 degrees. Wow, that's almost a whole circle. Find the radius of circle O. Let's do one more example. We're asked to find the area of this shaded region, which is a really unusual shape that we've never found an area of before. We're told that point O marks the center of the circle, and we're given this measure all the way across the circle, which is the circle's diameter. So I'm going to draw the radius of the circle, and I'm going to label it 4, since the radius is half of the diameter. This radius is also 4. Okay, now I'm going to label some regions in this circle. I'm going to label region 1, which I'm calling this region, this large sector of the circle. Region 2 here, and this will be region 3. And I know by the area addition postulate that the area of region 1, 2, and 3 added up must be the area of the circle. Okay, let's tackle region 1. We're told that this arc measure is 90 degrees. So by subtracting 90 from 360, we can find this arc measure going around this way is 270 degrees, which allows us to find the area of this sector here. So the area of region 1 is going to be 270 over 360, that's the fraction we're dealing with, times the area of the entire circle, which is pi times r squared. Okay, let's reduce this right now. 200 and, well, let's cross off these zeros. 9 goes into 27 3 times. 9 goes into 36 4 times. So I have 3/4 times pi times the radius squared. 4 squared is 16. And this simplifies nicely down to 4 goes into 16 4 times, so I have 12 pi for this large sector here. Okay, now to find region 2. And notice that we're told the measure of this, we're told the measure of this arc, which gives us the angle measure of this portion of the circle here. And 90 degrees is a right angle. So we are in luck because we have a right triangle here, and we know the legs are 4 and 4. So I can label the legs 4 and 4 here. And now we're down to a very simple problem, because in a right triangle, we don't have to find base and height. We know the base and height. 1/2 times the base times the height is going to be the area of this triangle. So that simplifies to 1/2 of 16, which is 8 units. Now, since we're asked for the area of just the shaded region, we actually don't need to worry about the area of sector 3 or the area of the entire circle. Starting off by writing down the area addition postulate is useful, but in this case, we only need 1 plus 2. So I'm going to stop right here and write down my answer, which is the area of region 1, 12 pi, plus the area of region 2, which is 8. And that's my answer. You try. Find the area of this shaded region,